Right now, as you sit there reading this, your engine is not resting. It is not waiting for the next drive. It is quietly destroying itself. Every time you turn the key, thousands of controlled explosions ignite inside your cylinders. But what most drivers never see is what happens between those explosions. Deep inside the engine block, where piston rings scrape against cylinder walls at thousands of cycles per minute, a microscopic war is taking place. Metal is not just touching metal, it is tearing it apart. This process has a name in tribology. It is called adhesive wear, and it is one of the most expensive and visible problems in modern engineering. Here's what makes it disturbing. Even if you are using premium synthetic oil, even if you service your car on time, even if you believe you are protecting your engine, you are not stopping this process. You are only slowing it down. At a microscopic level, the protective oil film breaks under pressure. When that happens, tiny high points on metal surfaces weld together for a fraction of a second and then rip apart as the piston moves. Each cycle removes atoms from your engine, not chunks, not visible damage, atoms. And this happens millions of times every single drive. You have felt the result, even if you did not recognize it. That slight delay when you press the accelerator, the way your car no longer feels as sharp as it once did, the steady drop in fuel efficiency that you blame on traffic or fuel quality, it is not your imagination, it is physics. And by the time most vehicles cross 80,000 miles, the internal damage is no longer theoretical, it is measurable. Compression begins to fall, not dramatically at first, but enough to matter. Engines at this stage typically lose between 8% and 15% of their original compression. By the time you reach 120,000 miles, that number climbs into the range of 18% to 30%. Compression is everything. It is the force that turns fuel into motion. Inside your engine, fuel ignites and expands, pushing the piston downward. But when wear increases the microscopic gaps between the piston rings and the cylinder wall, that pressure no longer stays contained. It escapes. Instead of driving your car forward, part of that energy leaks away into the crankcase. You're literally burning fuel that never translates into power. That is the hidden theft. Not dramatic, not sudden, but constant. Now here is where the story shifts from engineering to economics. Because this slow loss is not just a mechanical issue, it is a business model. The global automotive repair industry has grown into an $880 billion machine. Not because engines suddenly fail overnight, but because they gradually degrade. Dealerships and service centers do not sell you solutions to eliminate wear. They sell you maintenance cycles that manage it, oil changes, additives, engine restore treatments that promise improvement but wash away after a few thousand miles, temporary relief repeated indefinitely. The system does not profit from permanent fixes. It profits from controlled decay. And this is where most people never look further. Because they assume that if a real solution existed, something simple, affordable, and effective, it would already be mainstream. It would be marketed aggressively. It would be everywhere. But that assumption ignores a critical reality. Not every solution is profitable to scale. There's a material, a raw mineral that has been studied, tested, and quietly used in high performance and industrial environments for decades. It is called molybdenum disulfide. And unlike the synthetic additives you see advertised, this is not a laboratory invention designed for branding or subscription sales. It is a naturally occurring compound pulled directly from the earth. No patent, no exclusive rights, no corporate ownership. What makes it extraordinary is not marketing, it is structure. On a molecular level, MOS2 forms layered sheets that slide over each other with almost no resistance. Under extreme pressure, instead of breaking down like conventional oil, it bonds to metal surfaces, not temporarily coating them, but embedding into the microscopic imperfections created by wear. It effectively creates a solid lubricating layer that reduces friction at the exact points where oil fails. This is not theory. In controlled environments, MOS2 has been used in aerospace systems, heavy machinery, and high-load mechanical applications where failure is not an option. But in the consumer automotive world, its presence has remained strangely limited, often reduced to niche additives or overlooked entirely. Why? Because it does something that disrupts the cycle. It reduces wear, not for a few thousand miles, but at the source. It addresses the exact point where engines lose efficiency, metal-to-metal contact. Think about what that means in practical terms. If the primary cause of compression loss is microscopic wear between piston rings and cylinder walls, then a material that minimizes that wear directly protects compression. It slows the widening of tolerances. It reduces energy loss. It preserves the force generated by combustion instead of letting it escape. And in doing so, it attacks the root of the 30% power loss most drivers experience over time. And yet, despite its simplicity, despite its low cost, despite its proven physical properties, most drivers have never heard of it. Not because it does not work, but because it does not fit the economic structure of the industry built around gradual failure. So what you're looking at is not just a mechanical issue, it is a hidden system. a process where your engine slowly loses performance, your fuel efficiency declines, and the solution offered to you is always temporary. But beneath that system, there exists a different approach, one that does not rely on repeated servicing, one that does not degrade after a few thousand miles, one that comes from the Earth itself and operates at the exact microscopic level where your engine is losing its power right now. The story does not begin in a laboratory. It begins in pre-industrial Japan during the era of the Edo period, where craftsmen had no engines, no synthetic oils, and no industrial chemistry, but they had observation. They noticed something unusual about a naturally occurring dark mineral powder. When applied to moving wooden parts, friction almost disappeared. Axles rotated smoother. Heavy temple gates opened without resistance. Even ceremonial armor joints moved with a fluidity that defied the materials of the time. That mineral was what we now identify as molybdenite, the raw, unprocessed form of molybdenum disulfide. Long before modern science explained it, they were already exploiting one of the most powerful friction-reducing materials ever discovered. What they observed intuitively would take centuries to formally understand. Fast forward to 1957, when German chemists industrialized this ancient knowledge by stabilizing MOS2 into a liquid suspension that could be mixed with oil systems. This breakthrough laid the foundation for companies like Liqui-Moly, which built an entire product line around the compound. But even then, what reached the public was only a fraction of its potential, because while Europe was commercializing it, Japan was refining it in silence. By the early 1960s, engineers inside Toyota, specifically within their Nagoya engineering division, began quietly integrating MOS2 into internal fleet maintenance protocols, not as a marketing feature, not as a product, but as a controlled engineering advantage. Fleet vehicles treated with MOS2 demonstrated dramatically reduced wear over time, maintaining compression and performance far beyond expected service intervals. There were no advertisements, no public campaigns, just internal data and long-term reliability gains that would later define Japan's reputation for near-indestructible engines. And this is where the narrative separates from internet hacks and enters real science. Because the effectiveness of MOS2 is not anecdotal, it is rooted in its atomic structure. In the field of material science, MOS2 is classified as a transition metal dichalcogenide. That sounds complex, but the structure is surprisingly elegant. Imagine an endless stack of perfectly flat, hexagonal sheets. Each sheet is composed of a layer of molybdenum atoms sandwiched between two layers of sulfur atoms. These layers are tightly bonded internally, but the forces holding one sheet to the next, known as van der Waals forces, are incredibly weak. That weakness is the entire secret. Because when pressure is applied, instead of resisting motion like traditional materials, these layers slide over each other effortlessly, not breaking, not degrading, just sliding. This is why MOS2 behaves almost like solid graphite, but under far higher loads and temperatures. It creates a condition where surfaces that would normally grind against each other instead glide with minimal resistance. To understand the impact, you need to look at the numbers. In a typical untreated engine, steel components sliding against each other operate with a friction coefficient ranging from 0.4 to 0.8. That is the baseline resistance your engine is constantly fighting against. Now introduce MOS2 into that interface, and that number drops below 0.1. That is not a small improvement. That is a fundamental shift in how the system behaves. It means that the same mechanical movement requires significantly less energy, less resistance, less heat, less wear. In practical terms, untreated metal surfaces can be working up to 8 times harder than necessary just to overcome friction. But the most misunderstood aspect, and the one that elevates MOS2 beyond conventional additives, is what happens after it enters the system. This is not a fluid that simply circulates and washes away. Through a process studied extensively in tribology, MOS2 undergoes what is often referred to as a tribochemical interaction. Under heat and pressure, the particles are drawn to metal surfaces, particularly areas already affected by wear. They adhere to iron oxide layers and embed themselves into microscopic imperfections. This creates what engineers describe as a plating effect. Not in the traditional electroplating sense, but as a functional surface transformation. The metal is no longer exposed in the same way. Instead, it is covered by a thin, durable layer of MOS2 that continues to provide low friction properties, even under extreme conditions. And unlike oil films, which can break under pressure, this layer remains active at the exact points where engines typically fail. This is not speculative. It is backed by a massive body of research. The SAE International Database alone contains over 1,398 published papers examining MOS2 and its tribological behavior. A 2019 study published in the Journal of Tribology documented friction reductions of up to 26% under controlled conditions. A 2021 study conducted at the University of Technology, Sydney, further confirmed significant reductions in wear rates across treated metal surfaces, particularly in high-load environments similar to internal combustion engines. When you connect all of this, the picture becomes clear. Ancient craftsmen discovered the effect through observation. Mid-20th century chemists refined it into usable form. Japanese engineers applied it systematically to extend engine life. And modern science has spent decades validating the exact mechanisms behind it. This is not a shortcut. It is not a trick. It is a material solution to a mechanical problem, one that operates at the atomic level where wear actually begins. And that is the difference. Most solutions you are sold operate on the surface, temporary, consumable, designed to be replaced. But MOS 2 works at the interface where metal meets metal, where energy is lost, where damage begins. It does not mask the problem. It changes the conditions that create it. Now we leave theory behind and step into something far more dangerous to ignore: real-world data, not lab simulations, not controlled marketing claims. Actual vehicles, running under constant load, over years of operation, where failure is not an inconvenience but a financial liability. In 2009, a municipal taxi operator in Osaka made a decision that would quietly challenge everything the automotive service industry depends on. Their fleet consisted of 34 Toyota Corolla 1.8L sedans, vehicles known for reliability but still bound by the same laws of friction and wear as every other engine on the road. These cars were not driven lightly. They operated in dense urban traffic, constant stop-and-go cycles, long idling periods, and extended daily mileage that far exceeded private use. In other words, they were the perfect stress test for long-term engine degradation. The turning point came from a single conversation. The fleet manager was approached by a retired engineer who had spent 41 years inside Toyota's Nagoya plant. This was not a salesman, not a product rep. This was someone who had seen internal testing protocols that never reached the public. His recommendation was simple: implement a maintenance protocol using molybdenum disulfide at controlled intervals, not as a one-time additive, but as a consistent treatment aligned with oil service cycles. There was no marketing pitch, no branded product, just a mineral compound and a method. The fleet adopted it quietly. No announcement, no expectation of dramatic results, just a controlled trial across their vehicles. And then they kept going, year after year. Mileage accumulated not in thousands, but in hundreds of thousands of kilometers. Engines that should have shown clear signs of compression loss, increased oil consumption, and declining performance continued operating within normal parameters. By 2017, 8 years into the experiment, the fleet made a decision that turned this from an internal observation into undeniable evidence. They commissioned an independent inspection of their highest mileage vehicles. These were not lightly used cars. They had all exceeded 480,000 kilometers. Under normal conditions, engines at this stage would exhibit significant wear. Compression loss in the range of 20% or more would be expected. Power reduction, efficiency decline, and internal component fatigue would be standard, but that is not what they found. The compression readings came back within 6% of factory specifications, not partially recovered, not temporarily improved, maintained. After nearly 500,000 kilometers of continuous operation, the engines had experienced virtually no meaningful compression loss. The microscopic tolerances that normally widen over time had remained intact. The internal sealing that defines engine performance was still functioning at near original levels. This is where the narrative becomes impossible to dismiss, because compression is not something you can fake. It is not influenced by surface cleaning, fuel additives, or short-term treatments. It is a direct measurement of internal engine condition. If compression is preserved, it means wear has been controlled at the exact point where damage begins, between the piston rings and the cylinder walls, and the financial implications were just as striking. The MOS 2 treated fleet recorded an average engine-related repair cost of $112 per vehicle per year. In the same city, under the same operating conditions, comparable fleets running identical vehicles without this protocol averaged $340 per vehicle per year. That is not a marginal difference, that is a structural shift in maintenance economics. Across 34 vehicles over multiple years, the savings accumulated to approximately $43,000, not from reducing service frequency, not from cutting corners, but from preventing the wear that creates the need for repairs in the first place. And this was not an isolated case. A courier fleet operating out of Nagoya, again using Japanese vehicles under high mileage conditions, reported similar results. Honda CR-Vs in that fleet surpassed 520,000 kilometers while maintaining engine integrity, with repair costs measured at up to 91% below the industry average. Different vehicles, different operators, same underlying pattern. So now the question becomes unavoidable. If a $2 mineral compound can reduce wear to this extent, preserve engine compression over 500,000 kilometers, and cut repair costs by more than half, why is it not standard practice? Why is it not recommended at every dealership? Why is it not part of every maintenance schedule? The answer is not mechanical, it is economic. The global automotive repair industry, valued at hundreds of billions, does not operate on catastrophic failures. It operates on gradual degradation. The entire structure is built around predictable wear. Components slowly lose efficiency. Performance declines. Customers return for maintenance, diagnostics, and replacement services. The system is designed around repetition. Dealerships do not sell permanent solutions. They sell intervals. Consider what is actually being offered during a typical service visit. Fuel system cleanings, engine flushes, friction modifiers. Most of these products are designed to operate within the oil system temporarily. They do not bond to metal surfaces. They do not alter the underlying friction conditions at the microscopic level. And most importantly, they do not last. Within 3,000 miles, they are gone, circulated out, broken down, or diluted beyond effectiveness. That is not a flaw, it is a feature. Because a product that must be reapplied every few thousand miles creates a recurring revenue stream. A service that costs $200 to $300, repeated multiple times over the life of a vehicle, generates predictable income. Now, compare that to a mineral compound that costs a fraction of that amount and remains effective for significantly longer intervals. There is no subscription model in that equation, no repeat billing cycle, no long-term dependency. From a business perspective, it is not scalable. And this is why most mechanics never mention it. Not necessarily out of deception, but because the system they operate within does not prioritize permanent solutions. Training programs focus on approved products. Service menus are built around manufacturer recommendations and profit margins. Even well-intentioned technicians are working within a structure that rewards maintenance, not elimination of the problem. So what you're seeing is not a conspiracy in the traditional sense. It is a structural silence, a solution that exists, proven in real-world fleets, validated by long-term data, but incompatible with the economic model of the industry that surrounds it. And once you understand that, the pattern becomes clear. Engines are not designed to fail immediately. They are designed to wear gradually. Services are not designed to stop that wear completely. They are designed to manage it. And anything that breaks that cycle, anything that reduces wear at the source, preserves compression, and eliminates repeat maintenance, will always remain just outside the spotlight. Now we move from theory and proof into execution, because none of this matters unless you can actually apply it correctly. And this is where most people make mistakes. Not because the process is complicated, but because they either overthink it or skip critical steps that determine whether this works permanently or does nothing at all. First, sourcing the compound. You're not looking for generic engine additives or marketing heavy bottles filled with diluted friction modifiers. You need one specific thing, a colloidal suspension of molybdenum disulfide. That means the particles are evenly dispersed in a carrier fluid, small enough to circulate through your oil system and reach every friction surface. In the US and most global markets, the easiest option is Liqui-Moly Mo-S2 anti-friction engine treatment. A standard 300 ml can typically costs between $11 and $14. And when you break that down across oil capacity, it comes out to roughly $2 per effective application per cycle. In Japan, professional mechanics often use Waco Chemical Mo-S2, which operates on the same principle but is less widely available internationally. The key requirement is simple. It must explicitly contain Mo-S2 in suspension, not just moly-based marketing language. Now the application. This is where precision matters. Step 1 is the warm-up, and this is non-negotiable. You never apply this to a cold engine. Cold oil is thick, sluggish, and does not circulate effectively. More importantly, the metal surfaces inside your engine are contracted and not in their normal operating state. You need to drive the car for 15 to 20 minutes until it reaches full operating temperature. That means oil is fully thinned, internal clearances are stabilized, and the friction surfaces, especially piston rings and cylinder walls, are hot enough to accept the compound. This temperature condition is what allows the tribochemical interaction to begin. Skip this, and you are drastically reducing effectiveness. Step 2 is the pour. Once the engine is warm, leave it running at idle. Do not shut it off. Open the oil filler cap carefully and add the Mo-S2 suspension directly into the engine oil. For a standard engine with a 5 to 6 liter oil capacity, you use the full 300 ml can. This achieves the ideal concentration, approximately a 5% ratio of Mo-S2 to total oil volume. That ratio is critical. Too little, and you do not get full surface coverage. Too much is unnecessary and wasteful. If you are working with a smaller 4-cylinder engine with lower oil capacity, you adjust down to around 220 milliliters and keep the remainder for your next cycle. Once added, securely close the cap and let the engine idle for a minute or two to allow initial distribution. Step 3 is what separates this from every temporary additive you have ever used. This is the burnish phase. You are not done after pouring it in. In fact, the real process is just beginning. Over the next 800 to 1,000 miles, normal driving conditions, acceleration, deceleration, load changes, create the mechanical pressure required to force Mo-S2 particles into the microscopic irregularities of your engine's metal surfaces. This is not a coating that simply sits on top. It is a physical embedding process. The pressure between piston rings and cylinder walls acts like a microscopic press, driving the particles into the surface structure. At around 800 miles, the bonding process is approximately 60% complete. You may already begin to notice smoother operation, reduced engine noise, and more responsive acceleration. But the full transformation occurs closer to 1,000 miles, where the tribofilm becomes stable and permanent. At that point, it does not wash out with your next oil change. That is the critical difference. You're not reapplying a temporary layer. You're altering the friction characteristics of the metal itself. And now, the one warning that you cannot ignore. This protocol must never be used in motorcycles or any system with a wet clutch, where the engine and transmission share the same oil. The friction reduction properties of MOS2 are so effective that they will interfere with clutch operation, causing slippage under load. This is not a minor issue. It can render the clutch unusable. Standard automotive engines are completely safe because their clutch systems are separate, but shared oil systems must be avoided entirely. Now step back and understand what you have just done. With a process that takes less than 5 minutes of active work, using a compound that costs roughly the price of a cup of coffee, you have directly intervened at the exact point where engines lose power, efficiency, and longevity. You have not masked symptoms. You have not cleaned deposits. You have not delayed wear. You have reduced it at the source. In practical terms, you have just bypassed a system that would otherwise slowly lead you toward thousands of dollars in repairs. And this is only the beginning. Because what most people do not realize is that the engine is not the only place where friction silently destroys performance. There is another system in your vehicle, one that experiences constant load, continuous contact, and even higher stress conditions. A system where wear does not just reduce efficiency, it leads to complete mechanical failure. And buried inside Japanese engineering archives from the Showa era is a compound specifically designed to address that system. It reduces wear in CVT and automatic transmissions by up to 40%. It was tested, documented, and then quietly excluded from Western service manuals after 1988. So if you think what you just learned changes how you see your engine, the next revelation will change how you see your entire drivetrain. Subscribe, because in the next video, we are opening that vault.